Data replication is the process of maintaining copies of data at multiple sites. In essence, it involves creating and managing duplicate versions of information across different locations, ensuring that data is accessible and consistent, even in the event of failures or outages. It's like having backup copies of your important files stored in different places for safekeeping and easy access. Data replication is the process of storing data in multiple locations to ensure its availability and fault tolerance. It also improves read performance through load distribution and reduces network latency by placing data closer to users. In a typical setup, a primary database sends updates to one or more replicas, keeping them synchronized. This setup ensures that if the primary database fails, one of the replicas can quickly take over, minimizing downtime and data loss. The replicas can also handle read requests, distributing the workload and improving overall system performance. Data replication offers several key benefits. It provides high availability, which means the system remains operational even if some nodes fail, with automatic failover to replicas when the primary is down, supporting disaster recovery scenarios. It also leads to performance improvement, distributing read operations across multiple nodes, reducing network latency by placing data closer to users, and enabling parallel processing of queries. Scalability is another advantage, as it handles increased read workloads by adding replicas, supports geographic distribution of data, and enables horizontal scaling of read operations. Lastly, data replication ensures data protection with multiple copies that protect against data corruption, enable point-in-time recovery options, and support backup and archiving strategies. There are two main types of data replication: synchronous and asynchronous. In synchronous replication, data is written to all replicas simultaneously, and the primary database waits for acknowledgement from all replicas before confirming the write operation as complete. This ensures strong consistency but can introduce latency. Asynchronous replication, on the other hand, allows the primary database to confirm write operations immediately without waiting for replicas. Changes are propagated to replicas in the background, offering better performance but potentially leading to temporary inconsistencies. Each method offers a trade-off between consistency and performance, and the choice depends on the specific requirements of the application. There are several common replication topologies, each with its own characteristics. The first one is the primary-secondary setup, in which one primary node handles all write operations, while secondary nodes serve read operations and provide backup. Multi-primary setup enables multiple nodes to accept write operations, synchronizing changes with each other to maintain consistency. In chain replication, updates flow through a chain of nodes, with writes at the head and reads from the tail for strong consistency. Peer-to-peer replication means all nodes are equal, accepting both reads and writes, and changes are propagated to all peers in the network. Each topology offers different trade-offs in terms of performance, consistency, and fault tolerance, and the best choice depends on the specific requirements of the system. Consistency models define how data is kept consistent across replicas. One model is strong consistency, where all reads reflect the most recent write, regardless of which replica is accessed, ensuring that all replicas appear identical at any given time. In contrast, eventual consistency allows replicas to temporarily diverge, but they will eventually converge to the same state if no new updates are made to the dataset. Strong consistency guarantees immediate consistency, but has higher latency and reduced availability. Eventual consistency offers lower latency and higher availability, but there might be temporary inconsistencies. The choice between these models involves trade-offs depending on application needs. Data replication poses several challenges. The CAP theorem highlights the trade-off between consistency, availability, and partition tolerance in distributed systems, requiring replication strategies to balance these factors. Replication lag, especially in asynchronous setups, can lead to stale reads and inconsistent views of data. Conflict resolution is necessary when multiple replicas accept writes independently, requiring mechanisms like vector clocks or last write wins. Finally, network partitions can isolate replicas, forcing systems to decide between maintaining availability, potentially at the cost of consistency, or rejecting operations to preserve consistency, but reducing availability. Two common implementation strategies for data replication are log-based replication and state-based replication. In log-based replication, the primary node logs all write operations, then applies these operations locally and broadcasts them to replicas. Here is the pseudocode that has comments explaining the mechanism. In state-based replication, the entire dataset or just the changes are periodically synchronized, and the replicas merge the received state. Here is the pseudocode that has comments explaining the mechanism. Log-based replication captures every transaction, providing fine-grained control, while state-based replication simplifies the synchronization process by transferring the current state. The choice depends on the desired level of granularity and the complexity of conflict resolution. Several real-world systems implement data replication in various ways. MySQL replication uses a binary log in a primary-secondary topology and is asynchronous by default, with a semi-synchronous option available. MongoDB replica sets provide automatic failover, supports secondary reads, and utilizes oplog-based replication. Cassandra features a peer-to-peer architecture with multi-master replication and tunable consistency levels, using a gossip protocol for node discovery. Finally, Redis replication employs command propagation and partial resynchronization with asynchronous replication, and uses Redis Sentinel for high availability. Each of these systems implements replication differently based on its specific use cases and consistency requirements. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.